Another way to represent the edges in a graph is using what we call the adjacency list, which is an array of linked lists. So in every element in this array, we have a linked list, and this linked list contains the adjacent nodes or the neighbors of a given node. So instead of using a matrix to store all combinations of edges just to turn some of them on, we only store the edges that exist. Just like before, we have a hash table for finding the index of a node. So here the index of John is 0, and the first element in our adjacency list represents the neighbors of John. In our graph, John is connected to Mary, Bob, and Alice, so 1, 2, and 3 represent the index of these nodes in our graph, okay? So we're only storing the edges that exist. That's why this list is more space efficient than the matrix. What is the space complexity here? Well, in this array, we need one entry for each node. That's O of V. Now, for each node, we're going to have 0 or more edges. This can vary from one node to another. How many edges do we have in total? Let's represent that with E. So the space complexity of the adjacency list is O of V plus E. Now let's look at the worst case scenario. That's when every node is connected to every other node. We say we have a dense graph. In this graph, the total number of edges equals V times V minus 1, because every node is connected to all the other nodes except itself. Now, in some graphs, a node can also have a link to itself, but let's not worry about it now. The difference doesn't really matter. So the total number of edges equals V squared minus V. As you know, when we do complexity analysis, we only care about the parts that grow faster. So here we can drop the V and say the total number of edges roughly equals V squared. So our space complexity is going to be O of V squared. Now let's look at the time complexity of various operations. Let's talk about adding a node. To add a node, we simply add a new element in our adjacency list. This is an O of 1 operation. What about removing a node? Well, there are two things we need to do here. We should remove the corresponding element from our adjacency list and make sure no other nodes have a link to this node. So we have to iterate over our adjacency list and remove the target node from every linked list. What's the time complexity of this operation? Here we have V items. So iterating over the adjacency list runs in O of V. Now, in each iteration, we need to remove the target node from each linked list. Removing a node from a linked list is an O of N operation. But here the number of nodes in each linked list can vary. So how can we calculate the time complexity? Well, we don't really care about the number of nodes in each linked list. In total, if our graph has E edges, we're going to have E nodes across all these linked lists, right? So the time complexity of removing a node is O of V plus E. Now, what about the worst case scenario? This is when we have a dense graph where every node is connected to every other node. You learn that in those graphs, the total number of edges is roughly equal to V squared. So the time complexity of removing a node is O of V squared. What about adding an edge? Let's say we want to add a connection from Bob to John. Using our hash table, we find the indexes of these nodes. We go to the linked list for Bob and add a new node here. That's an O of 1 operation. However, before adding this edge, we have to make sure that this edge doesn't exist. So we have to iterate over this linked list and make sure the target node is not there. That's an O of N operation. If we say K is the number of edges a given node has, adding an edge runs in O of K. In the worst case scenario where every node is connected with every other node, we're going to have V items in this linked list. So the time complexity of adding an edge is O of V. Now, we have a special type of graph called a multigraph that allows two nodes to be connected via multiple edges. If you're dealing with a multigraph, we don't need to check for the existence of an edge. So adding an edge would run in O of 1. But in this course, we're just going to focus on simple graphs, not multigraphs. What about removing an edge? Again, we have to iterate over this linked list to find the target node and remove it. So that's an O of K operation, and in the worst case, it's going to be O of V. How about checking to see if two nodes are connected? Well, we need to iterate over the linked list for that node to see if the target node exists or not. Again, this is going to be an O of K operation with O of V in the worst case scenario. Finally, what is the time complexity of finding all the nodes adjacent to a given node? Again, we need to iterate over the linked list for that node, and that's an O of K operation. So if our graph is not dense, this operation is going to run much faster. We don't have to check every node in our graph. Now let's compare these two approaches side by side. The adjacency matrix takes significant amount of space, but if our graph is dense, we would have to allocate the same amount of space no matter what approach we choose. So let's look at the performance of various operations. Adding, removing, and querying the existence of an edge is faster when we use a matrix. All these operations run in constant time. When using a list, this is dependent on the number of neighbors of a given node. Finding neighbors, however, is faster when we use a list. We don't have to check every node in our graph to find the neighbors of a given node. Also, adding a node is super fast when we use a list. We don't have to recreate a two-dimensional array and copy items around. Removing a node runs in quadratic time in both solutions, so it doesn't really matter. Now, I know this was a fairly deep analysis. So which solution is better? Let me give you some pragmatic advice. All the time complexities you see here for the list are for the average scenario. Let's replace these with the worst case scenario where we have a dense graph. As you can see, if you have a dense graph, both these solutions take the same amount of space, but the adjacency matrix performs better. So if you're dealing with a dense graph, implement your graph with a matrix. Otherwise, use a list. In reality, the adjacency list is often better to represent graphs, and that's why we're going to use it in this course. Next, I'm going to show you how to build a graph from scratch.